Hello, welcome to today's topic. Today's topic will be oxidation and reduction reactions, otherwise called redox reactions. The objectives that will be covered in this topic will include 1. To investigate the action of common oxidizing and reducing substances in everyday activities. 2. To define oxidation and reduction. We'll do so 2 ways. 3. To deduce oxidation number from formulae. And finally, to distinguish between oxidizing and reducing agents. Let us begin. Let's talk a little about reducing agents in everyday activities. Now we know about chlorine, and that chlorine is used to wash white clothes. Now, when you use chlorine to wash your clothes, how does it work? Well, before we talk about chlorine working, let's talk about what is in your bleach. Now, if you look at this formula, this is called sodium hypochlorite, which is the formula of bleach. ClO- is the main ingredient in that bleach. Now, this is called chlorine bleach. There is another type of bleach that we call oxygen bleach, and this bleach consists of hydrogen peroxide. Of course, this one produces oxygen that is used to bleach the clothes. So let's talk about how bleach works. Well, bleach works by breaking the chemical bonds in the molecule. So the bonds are broken, and we're dealing with chemical bonds in this case. And these molecules are your stain. And of course, we know that stain produces color. So the bleach will break the bonds in the stain that is responsible for color, causing them to become invisible. So, in other words, they are not visible to the naked eye. So that's how bleach works. What about other type of oxidation going on in everyday activity? Now notice we say reducing agents, but here we're talking about oxidation. Well, we will discuss in great detail oxidizing and reducing agents with respect to oxidation and reduction. For now, let's talk about oxidation, because the bleach is really oxidizing the substance. And in terms of the browning of cut fruits, that process is also oxidation. But try and remember this. Whatever is oxidized is the reducing agent. So we'll get to the definitions later on, but for now, just remember that whatever is oxidized is the reducing agent. So have you ever observed that when you cut fruits, after a while they turn brown? What is the cause for that browning? Well, let's talk about browning effect for a minute. Browning of cut fruits is caused by the exposure of the enzymes on the surface of the cut fruit. And these enzymes, they are exposed to oxygen. And remember that oxygen is going to do the oxidation or the oxidizing. So oxygen causes oxidation. Remember that whatever is oxidized is the reducing agent. So enzymes are responsible for this chemical process, and it's called enzymatic browning. Cut apple and observe after a few hours what happened to the apple. You will see that it will turn brown. And if you cut a fresh apple, you will see the difference between the one that's cut earlier and the one that you just cut. So what caused that? Well, the enzymes create melanin. And as you know, melanin is a pigment in our skin. So black people, their skins are darker because of the melanin that is present in their skin. Now, the browning process, it can be slowed or prevented. Well, if you stop the enzyme or inactivate the enzyme from being oxidized by the oxygen, then the browning effect will not take place. So how can we stop this browning process? Well, you can stop it by heat. If you cook, the increase in temperature will cause the enzymes to now become denatured because the heat will denature the enzymes. Another way is by reducing the pH. In other words, if you lower the pH, these enzymes cannot operate in acidic conditions. How can you lower the pH of the enzymes? Well, you can rub lime juice or lemon juice onto the surface and it will not turn brown. So there are two ways you can reduce the browning effect: by increasing the temperature, one, and by rubbing lime juice or lemon juice onto the surface, which will lower the pH, making the enzymes unable to operate in that sort of condition. Let's continue with other types of reducing agents. Now, sodium sulfite or sulfur dioxide, these are used in food preservatives. Now, sodium sulfite is NaSO3 2-. So Na is plus and SO3 is 2-. So the formula would be Na2SO3. So this is sodium sulfite and it is a reducing agent. Now, sulfur dioxide is also another reducing agent, SO2. And now this is a gas. So sodium sulfite or sulfur dioxide, they are normally added to canned food or dry fruits to act as a preservative. Now, you should understand that when food spoils, it is because of the process of oxidation. So this process causes the spoilage of foods, but it can be slowed by using a reducing agent. So the oxidation process that causes food spoilage, we're going to cause it to slow down by adding sodium sulfite or sulfur dioxide, which is going to act now as your reducing agent. So how does this prevent the spoilage of food? If you look at oxidation, that process is going to cause the food to spoil. Well, the reducing agent is the substance that causes another substance to be reduced. So instead of being oxidized, the reducing agent is causing the substance to be reduced, which is really slowing down the oxidation process and preventing the spoilage of the food. So it really prevents the growth of the microbes. These microbes, when they grow and they oxidize, they cause the food to spoil. So if the sulfite or the sulfur dioxide is present, it prevents them from growing. And then you could say that the sulfite or sulfur dioxide, it possesses antimicrobial properties. That is, it works against the microbes. And that's how it operates as a food preservative. Now, as a preservative, it will maintain the color of the fruits or food and the flavor. Let us now discuss rusting and how it can be prevented. Now, rusting is a method where a metal combines with oxygen through a process called corrosion. Now, in this case, we will be looking at iron, forming iron 3 oxide. Now, this is the common name for rust, iron 3 oxide. Now, iron 3 oxide is formed when iron combines very easily with oxygen. Again, through what process? The process called corrosion. Now, iron 3 oxide is formed when the conditions are ripe for it to be formed. When do we have that? Well, you must have your iron, you must have water or moisture, and you must have oxygen. If all three are present, then you will have rusting. If any of these conditions are absent, then there will be no rusting. Let's look at a simple experiment. Here we have our apparatus set up. And in test tube 1, we have air and water, along with our iron. So you'll see that the rusting, the browning is taking place here. That's your rust. And as you can see, it is flaking off. So this is something that we'll discuss shortly. In test tube 2, you have your iron, but notice the water was boiled. What's the reason for boiling the water? Well, boiling the water removes dissolved oxygen. So this water is lacking oxygen, and we have oil on top to prevent any air from getting into the water. So in this case, we have one condition missing. We have water, we have our iron, and we have oil, which is preventing air from going in. So there is no oxygen, hence no rusting. In this case, we have calcium chloride, which is a drying agent. So the calcium chloride is absorbing any moisture that is found in test tube 3. So what do we have here? We have dry air, we have our iron, but we don't have any water. So this iron will not rust. As you can see, no rust. So test tube 3 is missing water or moisture, no rusting. Test tube 2 is missing oxygen because the water was boiled to remove any dissolved oxygen, so therefore no rusting. So test tube 2, no rusting. Test tube 1, we have rusting. Why? All three conditions are present. We have a nail, we have water, and we have oxygen. Hence, those conditions will cause rust to form on our iron. Let's write an equation for the formation of rust. So rusting is an oxidation reaction that we said earlier, and the iron will combine with water and oxygen, and it will form our hydrated iron 3 oxide, and we say that this is rust. Now the rust from the iron flakes off very easily, and if it flakes off, it is going to expose the surface below to more rusting, and that is why you see iron being eaten away when you have rusting, because the flakes will fall off, leaving the inner metal exposed to more oxygen and water, which is moisture, and that will continue to occur until there is no iron. All the iron will be eaten away. So the equation to form your iron 3 oxide is iron plus water plus oxygen will form your hydrated iron 3 oxide, which is rust. So you've been seeing the term oxidation, and we've been talking about reducing agents. So let's look now at some definitions of oxidation and reduction so we can get into talking about oxidizing agents and reducing agents. Let me say that there are more than 2 ways to define oxidation and reduction, but for the sake of the syllabus, we will stick to only 2 definitions for now. In this case, we will be discussing and defining oxidation and reduction based on the loss and gain of electrons and a change in oxidation number. So we'll discuss the 2 definitions in terms of these loss and gain, or increasing or decreasing of your oxidation number or oxidation state. Let's start with oxidation. Now, oxidation in terms of electrons. So, in terms of electrons, oxidation is defined as the loss of electrons. In terms of electrons, reduction is defined as the gaining of electrons or the gain of electrons. So while oxidation is loss, reduction is gain. In terms of a change in oxidation number, where your oxidation number will either increase or decrease, oxidation is an increase in oxidation number, while reduction is a decrease in oxidation number. So let's look at the two main points again. Oxidation in terms of electrons is the loss of electrons. Reduction is the gain of electrons. In terms of oxidation number, oxidation is the increase in oxidation number, while reduction is the decrease in oxidation number. I must say that there is a link between the loss of electrons and an increase in oxidation number, as well as a link between the gaining of electrons and a decrease in oxidation numbers. Let's see if we are correct. Look at, for example, magnesium. And magnesium is an atom. And you'll soon get the rules that states that magnesium, an element by itself in its free state, will carry a charge of 0 or oxidation number of 0. And magnesium will form magnesium 2 plus ion. Now going from magnesium solid to magnesium 2 plus ion, aqueous, what happened to electrons? Were they lost or gained? Let's try a simple method here. Now magnesium would have 12 electrons and 12 protons. So let me put 12 protons found in the nucleus. And I put my 12 electrons. At this stage, magnesium is neutral. So having 12 protons and 12 electrons, my charge will be 0. Now the configuration here would be 2, 8, 2. 2 electrons on the outer shell. So when will I form a 2 plus charge? Now note, in this case, I have 12 protons, which is positive, and 12 electrons. And so my charge is 0. So if I lose 2 electrons here, now my charge becomes 2 plus. So losing 2 electrons, I will put my electrons here on the right hand side of the equation. Now I lose 2 electrons, so my charge is now 2 plus. Now why did I put the electrons on the right hand side when we lost 2 electrons? Well, the reason for that is because if I put the electrons on the left hand side, I will not be able to get both mass balance and charge balance. So if I put the electrons here, then I'll have mass balance okay, but I will have my charge balance out of whack. I'll have 2 electrons on this side and a plus 2 charge on this side, and I don't want that. What I want is to have no charge on this side and no charge on this side. So having 2 plus and 2 minus, they will cancel each other to give me 0 on the right hand side of the equation and 0 on the left hand side of the equation. So whenever we have electrons being lost, it means that we are being oxidized. So we must put the electrons on the right hand side of the arrow. I'll show you shortly what happened when we are reduced. But look at this now. We said electrons are lost in oxidation. So we lost 2 electrons to form a 2 plus charge. If I lose 2 electrons to form a 2 plus charge, then I'll now have 12 protons and 10 electrons, and that'll give me a plus 2 charge. So you can see that I lost 2 electrons to form a plus 2 charge. I also increased in oxidation number from 0 to 2 plus. This is simply saying whenever you have loss of electrons, you will have increase in oxidation number. Let's check out reduction. In this case, let's start with iron 3. And we'll go to iron 2 plus. Now this is saying to me that I have 3 more protons than electrons. So if I'm to go from 3 plus to 2 plus, I must gain 1 electron. So as is, having 3 more protons than electrons, let's say we have 1, 2, 3. No electrons are there, so our charge is 3 plus. Now if I gain 1 electron, then these 2 here would cancel out each other and become neutral, leaving us with a 2 plus charge. So where do I put the electrons? On the right or on the left? Well, in this case, I did not lose electrons, so I cannot put any electron on the right of the equation. We gained an electron, so that must be placed on the left-hand side of the arrow. Now notice, in this equation, we have 1 magnesium, 0 charge, 2 plus and 2 minus, 0 charge. So we have both mass balance and charge balance. In this case, let's check to see if we have both mass balance and charge balance. In terms of mass balance, 1 Fe, 1 Fe. In terms of charge balance, I have a 2 plus here and a 3 plus here, plus an electron, which would cancel out one of my positive charges. So the charge on both sides here, this side will have plus 2, this side will have plus 2. Now don't get confused because you see me put in plus 2 and 2 plus and so on. Whenever you write a charge for your oxidation number on the formula, you must put the number before the sign. But in a statement where I'm saying that the charge is plus 2, the sign comes before the number. So on the atom or on the element, the number comes first. But in a statement, the charge comes first. Let's look at a few more examples. We're going to try copper 2, CO2 plus. Let's try H plus. Let's try Cl minus, Mg 2 plus, and of course aluminum. And we're going to see if in this case we have oxidation or reduction. Now let's check it out. Here we have copper 2 plus, and we want to form copper atom. Now to form copper atom from copper 2 plus ion, should we lose electrons or gain electrons? Now remember that this is simply saying that we have 2 more protons than electrons. So in order to become 0, I must gain 2 electrons. Now my 2 plus will combine with my 2 minus to form 0. So I have mass balance and charge balance. So my copper ion is aqueous and my copper atom is solid. Is this oxidation or reduction? Well, this is reduction. Why? It is reduction because 1, we gained electrons, and 2, we decreased in oxidation number from plus 2 to 0. So we have a decrease in oxidation number, ON. So copper ion was reduced to copper atom. Let's check out H plus and see if we have oxidation or reduction. So H plus ion is going to H2 and put our aqueous here. And let's check to see if we have mass balance. Well, I have 2 H's here and 1 here, so I need to put another one there. In terms of electrons, what do I need to do to move from 2 plus to 0? Well, I think we need to gain 2 electrons here. If we gain 2 electrons, we would cancel out these 2 positive charges, which would now give us a 0 charge for our molecule here. Again, this process is reduction. And notice, every time you have reduction, electrons are placed on the left-hand side of the arrow. Let's look at Cl minus. Cl minus is aqueous. And Cl minus forms Cl2. So let's balance this mass here. So we need 2 there. Now, what do I need to do to go from 2 minus to 0? Well, remember that this 2 minus is saying that we have 2 more electrons than protons. Do you realize that we don't really lose and gain protons? We only lose and gain electrons. So if I have less electrons than protons, we gain electrons. If I have more electrons than protons, we lose electrons. So in this case, I cannot gain any electron here because I can't gain proton to balance out the negative charge. But I can lose electrons to balance out the positive charge. So here, having 2 more electrons than protons, I am going to lose electrons. If I lose electrons, then that process is oxidation. So I cannot put electrons on the left. They must go on the right. So losing electrons, I'm going to add electrons on the right. And so I'll add 2 electrons here. Now notice 2 minus here and 2 minus on this side is saying that my charge is balanced. Of course, my mass is also balanced. So reduction for the electrons on the left and oxidation for reduction on the right. Why is it oxidized? Well, 1, we lost electrons. Or 2, we decreased in oxidation number from negative to 0. And if you're having problems in understanding going from -1 to 0, use the number line. So if you're going from -2 to -1, you are increasing in oxidation number. If you're going from 0 to -1, you are decreasing in oxidation number. So in terms of oxidation, 1, we lost electrons here, oxidation. And 2, we increased in oxidation number from -1 to 0. So this is going to increase in this way. That's oxidation. Look at Mg2 plus. Mg, solid. And of course, that's aqueous. So going from 2 plus to 0, we decreased in oxidation number. So from 2 plus to 0 is a decrease in oxidation number. That means that we are being reduced. So we must add electrons on the left to balance out the positive charge to get 0 on both sides. Going from Al to Al3 plus, it means that was 0. We must have lost electrons to go from 0 to 3 plus. How many did we lose? Well, we lost 3. So the 3 that we lost, we add it on the right to balance out the charges. So 0 and 3 plus and 3 minus, 0. So we have mass balance and charge balance. So no matter what type of equations we are balancing, we must have both mass balance and charge balance. Let's look at a simple way to remember the process of oxidation and reduction. Well, I'm sure that you're all familiar with oil rig, where oil simply stands for oxidation is loss, and rig stands for reduction is gain. So here we have oxidation, loss of electrons, or increase in oxidation number, whereas reduction is the gain of electrons or a decrease in oxidation number. So you've been hearing the term oxidation number. What do we mean by that? Let's examine the term oxidation number. Well, oxidation number simply refers to your oxidation state. This is your positive or negative number that corresponds to the charge on the element. So you saw where magnesium could be 2 plus, so the oxidation number will be 2 plus. You saw where H could be plus or Cl minus. These are all your oxidation numbers or your oxidation states. What you should understand is that metals carry a positive charge and non-metals would carry a negative charge. So, Nonmetals may not always carry a negative charge, as you see in the case of H plus here. So it may range from negative to positive corresponding to the group it is in. And we will be looking at different groups and rules for assigning oxidation numbers. So here are your rules for assigning oxidation numbers. Now they are not difficult, but you have to pay attention. Now, rule 1. If an element is in its free state, that is, it is by itself, its oxidation number is 0. So you saw where magnesium by itself was 0, H2 by itself 0, Al by itself 0, Cl2 by itself 0. As long as you are by yourself, you are 0. Remember that the elements that are diatomic, they cannot exist on their own, so they will bond to themselves, but they are still considered to be by themselves. Rule 2. An element in a compound and its valency preceded by a plus for metals or negative for nonmetals, for example, Mg2 plus and N3 minus. So the element in the compound, its valency will come after the number as long as it is on an element. Then you put the number, then the charge. Rule 3. An element in a radical, and again your radical is dealing with your polyatomic ion. So we say an element in a radical containing oxygen is equivalent to the Roman numeral in the name. For example, sulfur 4 oxide. Then the S in that sulfur 4 oxide is carrying a plus 4 charge. Or sodium dichromate 6. It is saying that the chromate ion is a plus 6. Or it is carrying a plus 6 charge. A simple one that you always hear about is copper 2 oxide or copper 2 sulfate. It is saying that the charge on copper is 2 plus. So as long as you see this Roman numerals in bracket, it is the charge on the element that it is in front of. Rule 4. The sum of all oxidation numbers of elements in a compound is 0. What do we mean by that? If I should write the compound magnesium chloride, then everything, all the charges or the oxidation state in this compound should equal 0. Remember that Mg come with a plus 2 charge and Cl with a minus charge, but I have 2 Cls, so I'll have 2 minus, and this is equal to 0. In the case of aluminum oxide, each aluminum carries a plus 3 charge, and each oxygen carries a minus 2 charge. So you'll see that Al is 3 plus here, and each oxygen will carry a 2 minus charge. So having plus 3 and plus 3, I end up with plus 6. And then having 2 minus 2 minus 2 minus, I have minus 6. And when you add those, you get 0, which means that the sum of the charges in a compound will be 0. Now, another rule that is very important is the sum of all oxidation numbers of elements in a radical or a polyatomic ion is equal to the charge on the ion. So notice in this case, ammonium ion is plus, so everything here equals plus 1. SO4, 2 minus here, or everything equals minus 2. And if I should write NO3 minus, then everything here equals minus 1. Please remember your charges when working in this topic of oxidation and reduction. The charge is very important, so you need both the sign and the number. Because if you put a number alone, I can't tell if you are increasing in oxidation number or decreasing in oxidation number. So remember that you must put your sign and your number when doing calculations in oxidation and reduction. So these are your basic rules. But you must understand that there are always exceptions to the rule. What are some of these exceptions? Let's see. Well, hydrogen is always +1 unless it is combined with a metal or carbon, where it becomes -1. So you'll see H plus. In HCl, the H here is +1, while the Cl is -1. You'll see where in ammonia, NH3, the H is with a nonmetal, so the H will carry a plus charge and the N carries a -3 charge. So simply put, anytime H is with nonmetals, it will always be +1. But if it is placed with a metal or carbon, it becomes -1. So +1 for all our H's with nonmetals, but as long as our H is placed with a metal or carbon, it becomes -1. That's our first exception. The next exception is in the case of oxygen. Oxygen will always be -2 unless it is in a peroxide. So if I have SO4, 2-, then the charge on oxygen is 2-. If I have CO2, the charge on oxygen is 2-. If I have sodium oxide, the charge on the O here is also -2. But now, if I form a peroxide, the O is no longer -2, it is now -1. That is the exceptions to the rule. And these are your exceptions to the rules. Now that we have an understanding of the rules of calculating and assigning oxidation numbers, and we know what the exceptions are, let us now start some calculation. To do the calculating of your oxidation numbers, we are going to use some simple methods. We are going to let X represent the oxidation number of the unknown element. In other words, suppose we have an element, but we don't know what group that element is in. If you know the group the element is in, chances are you will know the oxidation state of that element. For example, suppose the element is in group 1, then it will come with a +1 charge. If it's in group 2, it will come with +2 charge. If it is in group 7, it comes with a -1 charge. But if we don't know, then we will need to calculate it, and we are going to assign that unknown element X. 2, we are going to write the oxidation number of each particle in parentheses and the number of the particle outside the parentheses as shown below. And I'll show you what I mean by that. And then we will solve for X. Remember, we are not going to ignore our signs. Let's start some calculations. Here we have potassium permanganate, and we want to find the oxidation number of Mn. So that is our unknown. So what do? Well, we know that K potassium is present in group 1, so it will have a +1 charge. X is our unknown, Mn, and we are going to add now 4 times the oxidation number of oxygen. According to the rule, the sum of all oxidation numbers in a compound is equal to 0. Then we will carry out our math to get the answer for Mn, and we'll place the charges here. So you see where we have +1 plus our unknown X plus 4 times -2 equals 0. So +1 plus X minus 2 times 4 minus 8 equals 0. So X is equal to, we're going to bring the -8 over to become +8. So +8 here, and we have +1 here. So it's +1 plus X equal +8. Therefore, x is equal to plus 8 minus 1 equal to plus 7. So this is an example of one where the sum of the compound is equal to 0. And in this example, SO4 2 minus, you'll see that the sum of all oxidation numbers of elements in the radical here is equal to the charge on the ion. Now, what do we mean by that? Well, what is our unknown? We don't know S, so S here is our unknown. But we know that O is always minus 2. Please bear in mind that this 2 minus here is not the 2 minus for the oxygen. This 2 minus is the charge that governs both the S and the O. So in doing the calculation, we don't know what sulfur is, that is X, plus 4 times minus 2 for oxygen equal minus 2. Because the sum of all oxidation numbers of elements in the radical is equal to the charge on the ion. So therefore, X minus 8 equal minus 2. So X is equal to minus 2 plus 8, which is simply saying 8 minus 2 really, which is equal to plus 6. So the charge on S is plus 6 here. And we can check if S is plus 6. So let's put S there and put plus 6 here. And the O carries a 2 minus charge. Then 4 times minus 2 give me minus 8. Plus 6 and minus 8 is equal to minus 2. So we're okay with this particular example. Let's do some others. Let's do K2 Cr2O7, and we want to know the oxidation number of chromium here. Now we know that K is plus, so we have 2 of them, so it's 2 times plus 1 in your bracket. Plus 2x for our unknown, plus 7 times minus 2 equals 0 according to the rule. So we have plus 2 plus 2x minus 14 equal 0. So we'll say plus 2 plus 2x equal, and we bring the minus 14 over to become plus 14. And then we have 2x equal plus 14 minus 2, because we bring this plus 2 over to become minus 2. So really what we have now is 2x equal 14 minus 2 plus 12. So x now equal plus 12 divided by 2 is equal to plus 6. So the charge or the oxidation number on Cr2 here is plus 6. Let's try SO2. And let's find S. In this case, X is our unknown, plus 2 times minus 2 equals 0. Therefore, X minus 4 equals 0. So X is equal to plus 4. And that's our charge on S. Let's do NH4 plus. In NH4 plus, we know that the sum of the elements in the radical equals the charge on the ion. So we want to find N. So X plus 4 times plus 1 equal plus 1. So X plus 4 equal plus 1. So X equal plus 1 minus 4. And so X here is equal to minus 3. And let's try one last one. So you should be getting the basic idea already. So let's try 1HSO4 minus. So in this case again, H is plus 1 So plus 1, and we want to find S plus X plus 4 times minus 2 equal minus 1. So plus 1 plus X minus 8 equal minus 1. Plus 1 plus X equal minus 1 plus 8. So plus 1 plus X equal plus 7. So X now is equal to plus 7 minus 1, which is equal to plus 6. So the charge on S here is equal to plus 6. So we will take this principle in doing the same thing in working out the oxidation numbers in equations. So look at this equation. Magnesium plus oxygen produces magnesium oxide. Now, we know that if you are in your free state or by yourself, your charge is 0. So magnesium here is 0 and oxygen is also 0, but they move to 2 plus and 2 minus in the case of magnesium and the oxide ion. So going from 0 to plus 2, you'll have oxidation taking place here because there is an increase in oxidation number from 0 to 2 plus, while oxygen was reduced from 0 to minus 2. So here we have a decrease in oxidation number, hence reduction. Let's look at our equation. N2 plus 3H2. Let's put a 2 here, and that will give us 2NH3. So that's ammonia gas. Now we know that N2 is by itself, so that's 0. And H2 is also by itself, so that is 0. We know that H is plus 1, but we don't know this. So this we can work out here to assign the charge here to know what's happening in terms of oxidation and reduction. So you could go one side and say, well, X plus 3 times plus 1 equal 0. So X is equal to minus 3. So the charge here on N is minus 3. So let's check to see what is going on here. We see here where N2 decreased in oxidation state. So N2 to N here is minus 3. So here we have reduction. Whereas H2 increased in oxidation state. So here would have oxidation. Remember I said earlier that whatever is oxidized will be the reducing agent, and whatever is reduced will be the oxidizing agent. We will be looking at the definitions of oxidizing agents and reducing agents right away. So, now we're going to explain oxidizing agents and reducing agents. An oxidizing agent is a substance that causes another substance to be oxidized. So here we say the oxidizing agent is causing something else to be oxidized. In other words, it is taking away electrons from the substance, causing the substance to lose electrons. That is what we mean by the oxidizing agent is the substance that causes another substance to be oxidized. Now, if it is taking electrons, then itself is being reduced because it is gaining the electrons. So the simple definition is an oxidizing agent is a substance that causes another substance to be oxidized while itself is reduced. Remember, the oxidizing agent is causing the other substance to lose electrons by gaining the electrons. So itself will be reduced. And the same thing would apply for the reducing agent. The reducing agent is a substance that causes another substance to be reduced. In other words, the reducing agent is donating electrons. So if it's giving up electrons, the other substance will gain the electrons and become reduced, while itself, which is giving up the electrons, will be oxidized. So a reducing agent is a substance that causes another substance to be reduced, while itself is oxidized. So you will always see where the reactant that accepts electrons is being reduced, and that substance is called the oxidizing agent. So whatever is being reduced is the oxidizing agent. And whatever is being oxidized is called the reducing agent. In reactions where you have both oxidation and reduction taking place, we call that redox. Hence, we call them redox reactions. Here are some examples of oxidizing agents and reducing agents. So the common ones that you'll see potassium manganate 7, which is purple. You'll see potassium dichromate, which is orange. You'll see iron 3 sulfate, which is yellow or red-brown. And you'll hear about the conch sulfuric acid and so on. But in terms of the color changes, these are the main ones. Your reducing agents that is common would be your potassium iodide and your iron 2 sulfate. You'll see that hydrogen peroxide here, it can act both as an oxidizing agent and a reducing agent. But if it is with a stronger oxidizing agent, then it will act as a reducing agent. Or if it is with a stronger reducing agent, it will act as an oxidizing agent. And remember earlier you saw SO2, and SO2 is another example of a reducing agent. Metals are reducing agents. Why? Well, metals lose electrons. And if metals lose electrons, then metals are oxidized. And if metals are oxidized, then metals are reducing agents. And it goes to say then that most nonmetals which gain electrons, especially the group 7 elements, they would be considered to be oxidizing agents. Why? Because they gain electrons. And if you gain electrons, you are being reduced, which makes you an oxidizing agent. Now we have some good examples of oxidizing and reducing agents. How can we test for the presence of an oxidizing agent or a reducing agent? Well, hear this. You test for an oxidizing agent using a known reducing agent, as well as you test for a reducing agent using a known oxidizing agent. What do I mean by when I say known? Well, you would know the color change that would occur in that substance to say that if this change takes place, then this substance is being oxidized or reduced. That means that the other substance is causing it to be oxidized or reduced. Let's check out what I mean by that. Well, now we have our solution here. And this solution would represent our manganate ion. Now, manganate ion, which is MnO4 minus, is coming from KMnO4. So this ion is responsible for the purple color in potassium permanganate or potassium manganate 7. We saw how we calculated the oxidation number of Mn in the manganate ion to give us a +7 charge. So the charge on the Mn here is +7. So really, the reason for the color being purple is the +7 charge that is on the Mn ion. Now, this is an example of an oxidizing agent. Now, if I should add a substance to it, for example, hydrogen peroxide or hydrogen sulfide, and it changes color from purple to colorless, then it simply means that my manganate ion was reduced. If my manganate ion is reduced, then it must be reduced because of the presence of a reducing agent. So the reducing agent will cause it to go to Mn2+. Remember that a reducing agent is a substance that causes another substance to be reduced while itself is oxidized. So we see here where potassium manganate 7 changed from purple to colorless. So that is our observation. Let's look at some other tests. Now let's look at potassium dichromate 6. And we say acidified potassium dichromate 6. So we know that K2 Cr2O7 is our potassium dichromate 6. Now, what is responsible for the orange color? The orange color comes about because of the Cr2O7, where the Cr2 carries a +6 charge. Now, this is why it is orange. Now, in the presence of a reducing agent, remember that the potassium dichromate is an oxidizing agent. The reducing agent will cause the Cr2O7, 2-, to be reduced. So the +6 will be converted to Cr +3. And so +6 to +3, we have reduction. And hence, we have a color change from orange to green. In the event of I-, which is iodide ion, which is a reducing agent, if we should apply a substance, for example, an oxidizing agent, then the oxidizing agent will cause the iodide ion to increase in oxidation number. In other words, it is oxidized. Remember, the oxidizing agent causes the other substance to be oxidized while itself is reduced. And so you'll observe a color change here from pale brown to brown, where this is now your iodine and this yellow is your iodide ion. Finally, let's look at the last example. Here we see where this substance is pale green. And the fact that it is pale green, you can think of either one of two things that is green. Well, we know that Cr3+ is green, but we also know that Fe2+ is green. So in this case, we're dealing with Fe2+. Now, if Fe2+, being a reducing agent, is reacted with an oxidizing agent, the oxidizing agent will cause the Fe2+ to be oxidized, thereby increasing in oxidation state from +2 to +3. So the oxidizing agent itself will be reduced. So if we're using potassium permanganate, when it oxidizes Fe2 to Fe3, itself will be reduced from Mn +7 to Mn2+, which is colorless. So this is the basic idea behind the whole process of oxidation and reduction.